Hi, everyone. So this is the first of four biostatistics lectures for this course. You'll find that this lecture is probably review for most people. However, it is important to understand these concepts and to make sure everyone feels comfortable with them because they're going to serve as the foundation for all the kind of the future or the next lectures. So just to describe the lecture overview, first going to talk about why we use statistics and how we use statistics in pharmacoepidemiology. Then we'll review the different types of data, specifically focusing on discrete and continuous types of data or types of variables. And then to talk a little bit about how we describe data, and so how we use statistics or what we call descriptive statistics to describe data and some of the best practices for that. So why do we use statistics? And I'm a big believer in this, that statistics are tools and not rules. And so what I don't want people to do is necessarily memorize, or think that they have to kind of memorize, a bunch of formulas and things like that. What you should think about is how we might use statistics or how statistics might better our understanding for when we're looking at data or we're looking at study results and trying to then use statistics to make inferences and to inform our decision making. So statistics really help us understand our data, our observations in research studies. We can use them to describe patient populations, to describe the impact of an exposure or disease. We can use them to determine or predict the probability of our observations being due to chance. Okay, we want to be able to believe what we're seeing and have confidence in our results. We can use statistics to make determinations regarding whether or not groups are different. If we use drug A or drug B, how do we know that those results that we can that we can again believe those results and whether or not these groups are actually different or not. And so that's this last bullet as well is one treatment better than the other. So that's the term for that is comparative effectiveness, and something that obviously pharmacists will want to know when they're making decisions regarding a course of treatment. So when we think about applications of biostatistics, there's different things that we can do, and these are going to be, so this first lecture is going to focus again on what we call descriptive statistics, are using statistics to describe the world around us. There are also what are called inferential statistics, and that will be the second lecture in this series, where we're going to discuss something called hypothesis testing and also estimation. And you may be familiar with these already, but we'll go for them. And then, we're also going to look at the different types of statistical tests. That'll be the third lecture. And then the fourth lecture is going to be examining and quantifying the relationships between variables. So I don't have a bullet for the types of statistical tests, but these are the different lectures in this series. What do I want you to get out of these lectures? Again, it's the major concepts. It's how to, and what this whole course is designed to do is to help you, when you're reading or reviewing a research study, we want you to be able to critically appraise, the methods to be able to interpret the results. Okay, and so with regarding statistical methods, we want you to be able to not just skip the statistics section, but to read the statistics section to make decisions regarding whether or not they use the appropriate statistical test given the research question and whether those were appropriate or not. And then depending upon your how you look at that, how they then interpret, how you can then interpret their findings. I think often authors' interpretations are either incorrect or they're self-serving, meaning that the data are the results that they're reporting are not necessarily being kind of true to the data, and instead are kind of reinforcing some underlying hypothesis that they want to believe. So some basic concepts, but really important, as you'll see later, the types of data will determine the types of statistical tests we use, will determine the methods that we use to describe these data. So it's really important that you understand these kind of key, I think rather basic, but key principles. So the two main types of data are discrete data, which is sometimes just called categorical data. And these are, are variables that are characterized by, being able to be placed into categories. Okay, and so that's why we often will just say categorical versus discrete. We think of discrete data as being more qualitative. Okay, versus and the comparator here is continuous data, which we think of as being more quantitative. So continuous data are measurements that are made on a numerical scale. You can apply arithmetic to these two continuous variables to be able to describe them. And we're going to go through several examples of that. So within the types of descriptive data, there are what we call nominal data. Okay, and so you can see it right in the root there. This is naming or classifying observations into mutually exclusive categories. Okay, so nominal means naming. The categories don't have an inherent order to them. Okay, and so you can just look at some different examples, and so whether or not someone has a history of depression, and so the categories here are yes or no. We often, when we're using other types of statistical procedures, we'll assign values to these like 1 or 0. And so you'll often see that a lot. Other examples are like smoking status. You can be a current smoker, you can be a non-smoker. Okay, or vital status is something we often look at as someone is either dead or alive. Okay, so this is pretty straightforward. There are also what we call ordinal data. And in contrast to nominal data, there is actually an order to these variables. So you need to be cognizant of that when you're doing your analysis. So the categories can be ranked, are ranked according to some criterion. They don't necessarily have to have a consistent level of magnitude between the categories, but you do need to just make sure that you're looking at but they still have some kind of underlying order to them. So if we go back to our examples of smoking status, now you have current smokers, past smokers, and never smokers. And so there's not some kind of consistent level of magnitude between them necessarily, but you can see how there's an order to these, which describes how much exposure that people might have to cigarette smoke. Current smokers will have the most, past smokers will have had some, and never smokers will, have the least. Maybe they'll have some as secondhand smoke and things like that, but largely they should be the lowest. And so there's a clear order there. Socioeconomic status, again, this can be low, middle, or high. Often you'll see, and I'm sure you've done many of these surveys, where there's a Likert scale, and they'll have categories of whether or not you strongly disagree, you have no opinion, you agree, or strongly agree. Okay, so there's a clear order to these as well. In contrast to discrete data, we have what are called continuous data. And so again, these are data that are measured on a true numeric scale. There also is an inherent order to these data. But in contrast to ordinal data, there's a consistent magnitude difference between the units. Okay, so there's I think that makes sense. I don't need to give you another example. And as I mentioned earlier, these are capable of applying arithmetic to them, and you can also even have decimal values to them. You can have fractions of continuous data. One thing that's important to remember, because people will often try to take continuous data and make it discrete or make it, categorical. And the reason for that is that often there's an ease of interpretation than trying to understand what mean changes are or something like that you might see with continuous data. But the one important thing to remember is that you are losing information as you do that. So if you take an example of a continuous measure of blood pressure here with of 145 millimeters rather of mercury. You can then make these data, you can convert these, data into something that's ordinal, where this person then would fall into this kind of stage 1 hypertensive group, or you can just say that this person is hypertensive or not. And have this nominal or discrete data. But as you can see now, we don't know exactly how precise what that true measure is, which just means that there's somewhere in this, if you're looking at just this hypertension category, there's somewhere between 100, somewhere over 140. If we're looking at the ordinal data, we know that they have stage 1, but they're still going to be somewhere within that stage 1 data, versus if we actually have the precise measure in the continuous variable, that's where we have the most information. So this is something that people will often do, and often it makes sense, again, for ease of interpretation, but just something to remember, that when you convert continuous data to discrete data or nominal data, you're going to lose information. So how do we describe these data? What's a good way of letting people know? So if we were to measure the age of all the students in the P2 class, these are older data. So in case anyone's trying to figure out if this is actually your class, it is not. But we wouldn't want to just show this long list of numbers to people. And while they can get some information there, it'd be tricky to there's probably better and more efficient ways to describe kind of the distribution of age in the class. So the first thing is that what type of data are these when you look at these data? And I think go back actually, and I think most people would know that these are continuous data. Okay, there's 1 year, even though not every age is accounted for, there's 1 year between each unit, and so these are continuous data. Okay. How can we look at these data? Well, we can look at them actually categorically, where we where we break them into different categories just upon each age. So if we look at a frequency distribution of these different ages, and this is what output from a computer program would give you, you'll see that there was 2 people that were age 22. This is the proportion or the percent of people in the class that were 22, and then you'll see how this goes up. So there was 18 23-year-olds, which accounts for 20.45% of the class. Over here is what we call the cumulative percent, and this just adds everybody up so that you'll have 100 at the end of this category, so that you could say, well, there was 57.95% of the class was age 25 or lower. So there's different things. So these, actually categorizing these data this way is very useful, depending upon what your question is. Okay, if your question is what percent of the class was age 28 and under, this would be how you'd want to look at the data. Okay, so you can look at it as if the data were discrete. You can also plot the data, and so often when I'm doing analysis on research studies, that I'm conducting, I will plot the data and just see what it looks like. And we had a rather small number of observations in the P2 class, but sometimes we're looking at hundreds of thousands of patient encounters in different health systems, and so we can't just look at it in a table and try to understand what's going on. Plotting it will often give us very useful information about the distribution of these data. Okay, and so this is called a histogram, or sometimes they're called bar charts. You've seen them before. This is a histogram that Microsoft Excel will give you. So it's the same data, just plotted a little bit differently. And then we can also use what we call measures of central tendency. And so when you have continuous data, and so this only applies to continuous data, we can also report on things called the mean, the median, and the mode. And we'll go through each one of those. So the mean is just the average, okay? And I think everybody knows that. And we'll go through an example, but this is just the average of the full set of observations. One important thing to remember about the mean is that it's really can be strongly influenced by data, what we call data outliers, what we call extreme values. And so these are when you and we'll go through an example that shows you what happens when you have some of those data, and when that's the case, the mean might not be the best measure of central tendency to use to describe the data. Excuse me. Another measure of central tendency is what we call the median. And the median is the middlemost value in the set of values, or the 50th percentile. Okay, and so in contrast to the mean is relatively unaffected by extreme values. And so when your data do have extreme values, you have to decide how you want to treat them. If you believe that these are real data and you want to include them versus, an error or something like that, then the median may be a better measure to describe those data. And then the mode is just the most frequent value or values. Rarely do we, sometimes the mode is just reported if we think there might be some interest in what was the most frequently reported, value. But typically the mode is not reported in papers that you'll see. So here's kind of just a simple example using a really small sample of students, and how, and so these students were asked how many cups of coffee that they drank the night before their IDT exam. Okay, so kind of a silly example, but something that hopefully you can just like focus on the statistics and not pathophysiology, for example. So in this example, 4 students said they drank 2 cups. One student each said he or she drank 3, 4, 5, 6, and 8 cups of coffee, respectively. Okay, so how would you describe these data? So we can order the array. I know we used that term earlier in the slides, and the ordered array basically just means we take the data and we put it in order. Okay, that should make sense. So here's our 8, 6, 5, 4, 3, and then the 4 students that had 2 cups of coffee each. So we could describe these data in a figure. Again, this ordered array is fine because there's only 9 observations. But you can imagine that if we had tons of observations, that probably wouldn't be very useful. A figure is typically useful, but for this small number of observations, maybe it's going to be less informative. Or we can use our measures of central tendency. So here again is our ordered array. We can calculate the mean. When we calculate the mean, we're just adding up each of the individual values and then dividing by the total number of observations. And that's going to tell us that the mean coffee consumption the night before the IDT exam in this sample was 3.8 cups. Okay. We can report the median, which is the middlemost value. Okay, 3. So the median, the 50th percentile is 3. And then the mode was 2. Remember, the mode just represents the most often observed value. And so this here is like, there's 4 students said they drank 2 cups of coffee, and that's what you're seeing here. So the professor then, asked one more student how many cups of coffee he or she drank the night before, and the student replied 26. Now, this is clearly not, a real example. But what the point is here is that I want to kind of show you, even with a relatively small sample, what extreme values can do. And so we've now added this 26 cups of coffee to this measure to the data. So now we have 10 observations. Here's the ordered array. We can now calculate the mean, and the mean is now 6. The median is now 3.5, and the mode is still 2. Okay, so what happened? So we can look at these 2 data sets side by side and those results, and you can see what happened. Here's our first example where the highest was 8, and you'll see that the mean was 3.8. When we add this one extreme value, just one additional observation, you'll see now the mean jumps all the way up to 6. whereas the median doesn't change very much at all. It was 3 before, and now it's 3.5. Okay, it's this 50th percentile in between the 3 and the 4 here, and the mode doesn't change at all. So a very simple example, but it's just supposed to illustrate, again, that how easily the mean can be affected by extreme values. And as a result, we won't necessarily want to use the mean to describe, to describe data that look like this. And so we're going to talk about that next. So again, how does this affect your data analysis? And this is important because we're usually only going to present the data one way. So we're not going to usually give the mean age and the median age. You usually do one or the other. When you read papers and people are providing, the mean, the median, and the mode, or again, I've never seen the mode necessarily written that way. It basically means that people might not know what they're doing and how best to describe these data. And as you'll see soon, this also affects what statistical test we use. So here we have the distribution of weight in a fourth grade class. Again, this is just an example of showing you how data can be distributed. What we're really looking for here is do these data have extreme values? Are these data what we call normally distributed, or are these data skewed? And so, and sometimes this can be a little bit tricky, but this is a decision that you're going to have to make early on in your analysis, and also when you're when you're looking at papers and reviewing studies, is whether or not the data were skewed and did they use the appropriate statistical test. Data can take all different types of distributions. Sometimes there's this uniform distribution where it was, the observed frequency is the same across all these different values. Sometimes the data can be what we call negatively skewed, okay, or skewed to the left. Sometimes data can also be skewed to the right. The example that I often use for data that are skewed to the right, our coffee example it is those types of data where most of the people were all up in this area, but we had this one person all the way out here that had those 26 cups of coffee and that are then throwing off, the distribution. Another example that we see a lot in some of my research studies is when people are, when we're looking at hospital length of stay. Most people come into the hospital and they're hospital for, 2 to 3 days, and then they're discharged. Okay, but we do have often have people that are, just a few people that will sometimes be in the hospital for 100 days, and as a result, that really skews the data and pulls the mean, kind of further out here and is not, very representative. So anytime we talk about length of stay in the hospital, acute care length of stay, we almost always report the median and not the mean. Costs and triglycerides and are some other things that are often kind of what we call positively skewed. And then bimodal distributions you sometimes see when you're looking at something like a infectious curve at an outbreak, and you have secondary transmission, and you're looking at kind of time since exposure, the initial exposure. It's because that sometimes these people are catching some communicable disease from these people, so you'll see these types of distributions as well. So here's just an example. So, and this is, this comes right from the kind of the supplemental reading. If you want to, go look at that. So which measure of central tendency would best represent the data in this example? And so, there's only 10 observations. These are continuous data. So looking at someone at height, okay? And you can see that there's they present a mean, a median, and a mode values. And so how do you make a decision based on that? Well, if the data are normally distributed, then the mean and the median are going to be pretty similar. Okay, and so in this case, they are. The data are pretty similar in that the mean and the median are pretty similar in that the mean is 55, the median is 54.5. And so I think we can fairly safely conclude here that the mean is the best measure of central tendency. What about these data? So for these data, again, we don't see any values on here, but we can just look at the distribution of the data. And so, I mean, this is just a almost perfectly bell-shaped curve. And so again, the mean is going to be somewhere in here, and so is the median, right? This is going to be the 50th percentile, but it's also going to be the mean. So as a result, the mean is still the best measure of central tendency. Now you can say, why don't we use the median? And I think there's reasons for that. And because the type of statistical, again, the type of measure of central tendency that you're using is also going to influence what type of statistical test that you use. And as I'll describe in the third lecture in this series, you know, when you actually are using the mean when the data are normally distributed, those statistical tests tend to be generally more powerful than tests where you're what we call non-parametric tests when the data aren't normally distributed. And so, sorry, that's a little bit of a jump ahead, but this is something that this is another reason why you can't just use the median, or why you certainly can, but you know, here we're asking what the best measure, and the best measure here is the mean. So here's another example, and here the data are now skewed. Okay, this is like our length of stay example, and that's the kind of an easy one to remember. And here, you can see that the median is here, the 50th percentile. The mean gets pulled way out here due to some of these extreme values. And so the median here, when the data are skewed, is going to be the best measure. Okay, so here's another example. And so we're seeing like bell-shaped curves, but like they're of all different shapes. And so as we'll describe it in a moment, what this means is that, you know, the mean is still the best measure here, okay? But that the data are really spread in this like curve, for example, or this one, the data are really spread out around the mean. So there's a lot of what we call dispersion. There's a lot of variability around the mean, but the data are still normally distributed. Here, the mean is still the best measure, but there's not as much variability. There's not as much dispersion. And so the mean is still the best, just to be clear, the mean is still the best measure of central tendency for these data. So now we're going to talk about dispersion. We just saw that in those bell curves there. And you know, not only do we typically want to know kind of what the best measure of central tendency, we want to know how the data are spread around that, okay? Because that can also give you lots of information. And to do that, we can calculate something called the variance, okay, which is the average squared distance between each observation and the mean, or the standard deviation, which is the square root of the variance, and that's what's often reported. Okay, so let's do that for our coffee drinking example. Here we have our ordered array. You can see this kind of diagrammed here with our observed mean of 3.8. These are the values that were less than 3.8, with, you know, kind of a bar showing, you know, illustrating kind of how far from the mean they were. And here are our values that were above 3.8, okay, with the same error bars. And so the formula is you know, it's illustrated here, and you can calculate standard deviation, which is 2.2. And you know, almost, you know, when you report the mean, you should always also always report a measure of dispersion, okay? And so that should be the standard deviation. Okay, so how would you describe these data? We would say that the, you know, coffee consumption among the P2 class prior to the night before their IDT exam was a mean of 3.8 cups with a standard deviation of 2.2 cups. You know, when you look at measures of dispersion, sometimes people will just give the full range, which is called, you know, the largest value to the smallest value, okay, and just the difference between them. But more often, we use something called the interquartile range, which is the difference between the 75th and the 25th percentiles. This is abbreviated as IQR. And you can either report the individual numbers associated with the 75th and 25th, or that sometimes people will just actually do the subtraction and just report the difference. Okay, so for our ordered array again, we can report that the 25th percentile was 2, the 50th percentile, which is the median, was 3, the 75th percentile was 5.5, and then the 100th percentile was 8. The full range of these is 2 to 8, or the difference between them being 6, and the IQR is 2 to 5.5, and the difference between them is 3.5. Okay, so if these data were skewed, then we were to report the median, we would also report this IQR. So again, just to reinforce that, what I said is that when the data are normally distributed, we report the mean and the standard deviation. And when the data are skewed, we report the median and the interquartile range. Okay, please remember this. This is important. All of this, again, when we talk about kind of normally distributed data, this is just a standard normal curve. Okay, and if the data are normally distributed, then basically 68% of the data should be within one standard deviation of the mean. Okay, here's the mean here in the middle. And 95% of data should be within 2 standard deviations of the mean. And 99% of data should be within 3 standard deviations of the mean. And you don't have to memorize this, but just kind of showing you, again, what these distributions look like. Okay, so we're going to take a break from continuous variables, and we're going to talk about categorical variables, which are, I think, easier and more straightforward. The mean, the median, and the mode are not appropriate to describe categorical data. Okay, we can't add them up and divide them. And instead, we use something called frequencies, proportions, and percentages. So here's an example describing categorical data. So data were collected on smoking status. So either a current smoker, past smoker, or never smoker from a sample of 24 family medicine patients. And the count responses for each category. So 18 patients said they never smoked, 4 patients said they were past smokers, and 2 patients said they are current smokers. And you can calculate the proportion and percentage for each category. Okay, so proportion is of these never smokers, it's going to be 18 divided by the total number of people, which is 24, 18 over 24. And so that's 75% said they never smoked. 8 over 24, or 17%, said they were past smokers, and 2 out of 24, or 8%, said that they were current smokers. So just to summarize types of data and ways we describe data, just remember that there's different ways to present data, and and to know that there's different types of data. So being categorical or discrete and or continuous. And it's important to recognize that when among continuous data, how are they distributed? Are they normally distributed? Are they skewed? For continuous data, if they're normally distributed, we want to report the mean and the standard deviation. For skewed data, we want to report the median and the IQR. For categorical data, we want people to, you should be reporting proportions and or percents. And just remember that you can sometimes take categorical data or continuous data and make those data categorical. So we talked about this, early on in the lecture, but this is often done to ease interpretation of results. But it can, I think, again, you're losing information. So you should make sure that you're very thoughtful when you do this. You should use clinically relevant cutoffs or base them on the distribution of the data. So sometimes people will divide the data at the median into two groups for further analysis. And then, as I've kind of said many times, you lose information when going from continuous to categorical. So that's the end of this lecture. I look forward to seeing you in lecture 2.
Thank you so much.